advanced imaging mode. Before we start, I always like to say something about who we are. We are basically former employees of Agilent Technologies. We're 5 application engineers, application scientists, and repair engineers. So we like to support existing instruments and hopefully support this instrument for another 10 years. We have enough parts and enough expertise to do that. And these are the websites. The Zoom AFM is the front end of this, that you can come to Zoom AFM. You can always talk to me, and you can always talk to one of our application scientists and application engineers. We're here. We'll take your question, answer your questions. It's good opportunity to connect. HomeQ SPM Service was a business that started by Steve Rubber, and he is a production engineer and a service engineer. He can repair things. He has enough parts to repair the instrument for the next couple of years, 10 years, hopefully. NanoQ Technology is my business, and I actually started to invent a lot of modules for this atomic force microscope, and then some of the modules not only for AFM, but also outside AFM. CSI Instrument is a company started by another employee in France, and they build their own AFM, and their controller can drive the old AFMs too. Okay, advanced imaging mode based on oscillations. So atomic force microscope had a lot of the imaging modes are based on oscillation. The entire tapping mode is actually based on oscillation. So I have this logo of this different kind of waveforms there. So yeah, we're going to touch a little bit about basics of tapping mode, which everybody's familiar with, and then we push this forward to long-range force interactions. That is advanced imaging mode is about. And then we will say something about the AFM sample modulation technique. Okay. So basic force interaction of tapping mode. Tapping mode is based on the actual force interaction between the physical tip and the physical sample. When tip and sample get into very close to each other, they're actually experiencing strong attractive force and then quickly turn into strong repulsive force. And this strong attractive force and repulsive force when tip and sample in very close distance are the basic forces that we use to do tapping mode and non-contact mode. Okay, so when the tip and sample get into within 10 nanometer range, there will be strong attractive force, and as tips get closer and closer to the sample, the forces become more strong. Repulsive force is when tip is actually invade the sample, and then the attractive force turns into repulsive force, because basically you cannot have two objects occupy the same space. They're mutually exclusive from each other. Two baby put in the same place, they start to push each other. Close range force. I had a early presentation talk about this tapping mode and then non-contact mode and so on and so forth. And this is not the focus of today's presentation. Just say something quick is that when tip and sample getting too strong attractive, there's a strong negative force gradients, and when tip and sample getting strong repulsive, there's a very sharp repulsive positive force gradients right here. And this force gradients cause the resonant peak to shift, and by detecting this shift cause the amplitude change. That's the feedback input of the tapping mode and true non-contact mode. Okay, that's not today's focus. Today's focus, let me go forward, is the detection of long-range force that it can be imaged with the atomic force microscope. And first of all, let's define what is long-range force. Long-range force, in our case, are the force that beyond when Van der Waals force beyond 10 nanometers. Let's say a couple of 100 nanometers to a couple of microns. Those are long-range force. And these long-range force includes magnetic force and electrostatic force. These are long-range force. These force exist when tip and sample are a little bit far away from each other. So this is the same graphics, same curves that I draw as a short-range force that tapping mode and true non-contact mode is based on. However, there's a long range force always overlap with it. For example, tip sample, when it's getting further distance, you still have a long force slope. One is magnetic, the other is electrostatic. Magnetic force imaging. How do we image magnetic force? What's the basic physics of imaging magnetic force? The way to do that is that, first of all, magnetic force, it was imaging using what we call the interleave mode or lift mode. In other words, to detect the long range force. Because one reason for to do interleave is that when tip and sample was very close to each other, the short range force is much stronger than the long range force. Right? You could fall from a 10-story building and hit the ground. You take like dozens of feet, and then that acceleration only takes a split of millimeters to stop you. So the contact short range force is very strong, and long range force is relatively weak. To sense the long range force only, you have to separate the distance, so the short range force does not impact oscillation. So in other words, you need to do what we call interleave mode. Tip and sample has to have a separation distance, and therefore you sense the long range force when the short range force disappear. Okay, the way to detect the magnetic force is to, first of all, you have to use the magnet to detect magnetic force. So the tip is actually coated with a permanent magnetic material coating and magnetized, some kind of cobalt alloy. So the tip is actually a little magnet. And when tip is a little magnet, it will sense the magnetic force on the sample, and this sensing of force can be detected at a relatively long separation distance, for example, 50 nanometer all the way to a micron, or even several microns. Okay, so tip will scan the sample twice. The first time will be on the sample, detect the surface topography, and second time, the instrument will remember the first topography movement of the tip, and then lift the tip, and with a separation distance, scan second time. And then when you scan second time, the magnetic force, or to be precise, the force gradient, cause the oscillation resonant frequency to slightly shift. By detecting the phase shift of the second scan, you recorded the magnetic force. That's how it was done. Okay, so these are examples of the magnetic force microscopy imaging. The one on the left is the image from a hard drive. Basically, those stripes are magnetic information written on a hard drive. The one on the right are these little mini nano, 10, 20, 100 nanometer little magnets. And then these magnets has north and south. You can see one side is black, the other side is white. These are the recording of the magnetic force, repulsive and attractive. And some of the magnets are reversed. So these are imaged using what we call left mode. The image will scan sample twice. First time on the sample, second time lift with a separation distance. The image on the upper left corner is actually stainless steel. Stainless steel is basically an alloy made of different kind of grains, and these grains are made of cobalt, iron, nickel, and these grains will to present different magnetic field. The one on the right is the same image that I displayed before, basically the magnetic little domains. Okay. Other than the magnetic force, you could also detect electrostatic force. There are different ways of detecting electrostatic force. Here are different ways. Interleave EFM was DC bias. Interleave EFM was AC bias. And then scanning surface potential imaging. And then we could also use multiple lockings. These are all different variations of this same technique. Okay, so what is the DC bias EFM? The working principle of DC bias EFM is relatively simple. If the sample has charges on the surface, and here I have little Chinese left in there. I forgot to change. This is 电荷. That means electrical charge. Okay. So you have some charge on the surface, and then if your tip is also have a little bias to it, right, a little charged, then this charge on the tip will cause an attractive and repulsive force between the tip and sample. And this attractive repulsive force is of very similar nature of MFM. And then you tip scan the sample twice. First time on the surface to image topography. Second time was a lift separation distance. So the tip glide over the sample and then recorded the attractive repulsive force from the phase image. Straightforward. Now, this straightforward imaging mode works very well until that you try to the limitation of this imaging mode is that it does not detect the charge that's very, very small. That's because of noise, because the tip has an oscillation, and if a charge is very small, the oscillation caused the oscillation caused by the charge is very small, and then you have very low signal to noise level. It's very, very, very hard to detect a very small signal in a big noise. In this case, even you have cantilever in the air, nothing disturb it. There are a certain amount of Brown motion of the cantilever that caused the tip have oscillated with noise. So how do we overcome this detecting a very small attractive repulsive force with a large amount of noise? People in electrical engineer will understand this principle. Working principle is that it is very hard to detect a small DC signal. However, if your signal is AC, you could detect it much easier even in a very noisy environment using a technology. It's called locking amplifier. And locking amplifier will lock on to a particular frequency of signal. And even the signal to noise level is 1 to a million, it can pick up that particular signal. Okay, so one way to turn this EFM from DC bias to more sensitive is to bias the tip with not DC but AC. So instead of trying to put a DC bias cause the tip sample have attractive force, I will apply an AC tip bias. This AC tip bias will cause the tip to sense the electrical charge of the sample with a vibration at the same frequency of AC bias. And then you can, using locking amplifier, to lock onto that AC oscillation. And then this you can detect signal in a much smaller signal in a bigger noise. And that's the base of the what I call interleave mode EFM with AC bias. Basically, it's bias in AC, and then you detect oscillation at that particular frequency. Here, another reason that it uses interleave mode is that the early AFMs has one lock amplifier. This one lock amplifier is used to detect the sample topography using tapping mode in the first scan. And when it does the second scan with interleave mode or lift mode, it needs to switch to apply a bias, not apply to the piezo oscillation. Here, look at the signal route. The signal route to different places. Here on the lift mode, it route to the cantilever bias. I'm going to skip this KFM part because later on I'll also talk about the working principle of KFM using the single pass. So a single pass EFM-KFM was a double lock-in. This is a much later technology. Is that the lift mode works well with one single lock-in. However, tip and sample has a separation distance. So when tip lift over the sample, there's a separation distance, and your resolution cannot surpass the separation distance. The further you separate, the less resolution you will get. So single pass EFM-KFM using multiple locking. Basically, the AFM will using two lock amplifiers. One is to oscillate the sample at one particular frequency, and then it does tapping mode to record the topography. At the same time, it will use a separate frequency to apply an AC bias to the tip. In other words, the tip will sense the AC electrostatic force with a different frequency. So tip will oscillate at two separate frequencies, and therefore the AFM can scan the electrostatic force imaging and then topography at the same time, and that's what we call single pass imaging. Let's talk about the basis of the Kelvin force microscopy. The Kelvin force microscopy is a derivative of the electroforce microscopy. And then here is the basic math of the electroforce microscopy. Here, the force represented by the potential difference between tip and sample is phi, and dc/dz, phi a square. Okay, this is the basic Coulomb formula. Okay. But when we do little math and put a time in it, because your AC bias has a time factor here, omega t is a time factor, it's a sine wave, it's a time factor. And then this is the formula. And then here you have the sample's potential, which is phi. And then the difference between sample potential and tip potential, which is UDC, which is the DC component of the bias, and then UAC, the AC component of the bias. Sine omega t is the oscillation. Okay. And you open this up into three factors, three formulas. The first formula here, dc/dz, phi minus UDC and plus whatever it is. This is the static force. This is the force that we use using DC bias to detect the EFM. Okay. There's no time here. In other words, this force does not oscillate. It's a DC force. It's very hard to detect. Then you have the second factor here. Second formula is dc/dz, phi UDC, the difference here times UAC and sine omega t, which this force will oscillate at the same frequency of your bias voltage. And the force, the oscillation amplitude is determined by two factors here. One is UAC, which is the AC part, the AC peak to peak, and the potential difference between your tip and sample, the DC part. What if we put a feedback loop here? We can put a feedback loop to control the UDC so that this force is near zero. It's nullified. Using feedback, we change UDC so this F omega is minimal, is zero basically. When that happens, you know that the DC component of the bias to the tip is actually equal to the potential in the sample. You output this signal to another channel, and then this channel is your surface potential imaging. Okay, so that's the basics of Kelvin force microscopy. Basically, it'll use the oscillation as a reference, and then you nullify the oscillation by modulating the UDC, and then you output the UDC, and that's the imaging of the surface potential, and we call this Kelvin force microscopy. Okay, that's the base of it. Kelvin force microscopy is a quantitative measure of the surface potential, and not only that, you have the third formula here, factors here, is the dc/dz and then UAC square and times omega 2 omega t, cosine 2 omega t. This is a double frequency force. Okay, in other words, tip will be oscillated by sample at double the frequency also, and this double the frequency is proportional to your dc/dz signal. In other words, this signal output is your dc/dz. We give a name as the capacitance gradients between the tip and sample. Okay, so this is the Kelvin force, and this is the double frequency. Double frequency measure your how do I call it, permeability, or how do I say the capability of the sample being how do I say this polarized by the tip. Productivity, yes, yeah. Okay, so in layman's term is that when we apply an AC voltage to the tip, when the tip is on the positive, it will polarize the sample, negative, positive. When tip reach a negative peak, it also polarizes. The polarization of the sample will flip, and then either on the positive peak to the negative peak, the force between tip and sample will peak. will become maximum. In other words, the maximum force is reached in twice in one period of this oscillation. So the tip is oscillated or sends the force at double the frequency, and this double frequency is a measurement of the polarization of the sample. This is the wiring of the single pass. The lock amplifier that we use has three lock amplifiers, 1, 2, 3. Number one, we use it to oscillate the tip to do tapping mode. We take the deflection signal and then write them into lock-in amplifier number 1 and put in the servo. That's your tapping mode. And then you take the same deflection signal, you route into lock-in number 2 and put into the KFM servo feedback, and therefore it'll output into surface potential imaging. And that's the we also have the lock-in number 3 log on the second harmonics, the 2 omega to output the DC-DC signal. This is an application that I did some years ago. These are amazingly, those are carbon nanotubes grow on the surface like a toothbrush. These nanotubes are actually standing up. And then at you can see that the second image on the right is the hair color is represented by surface potential. And you can see some nanotubes lying down on the background, and then most of them are standing up. And when you zoom into that, you can actually see the end of those carbon nanotubes. And this is very high resolution. This is one more step more advanced than the single pass. This is called the frequency modulation detection Kelvin force microscopy. So basically that we'll not only detect the oscillation, but also we detect the gradients, the phase shift, or in other words, the resonant frequency shifting because of the force gradient between the tip and sample. So instead of route the deflection signal, we route the phase output from lock-in number 1 to feed into lock-in number 2. And therefore, we're actually detecting the shifting of the primary resonant frequency. Why we want to do that? So in this variation of the imaging mode of single pass KFM, we actually not detecting the force by detecting the force caused oscillation. We're actually detecting the force gradient of the electrical force by detecting the resonant frequency shift of the primary resonant frequency. This gives us a very high spatial resolution and then very low, very high signal to noise level. And here's some examples of that. I actually have a much more interesting data I forgot to include here. This is alcan. This is perfluorine alcan self-assembly. Those little flowers are perfluorine alcan. They're alcan carbon chain assembled on the surface. Part of the molecule, the hydrogen, is replaced by fluorine, and fluorine is extremely electronegative in chemistry class. We learned that it will actually attract electrons from the silicon and induce a very strong negative electrical charge around itself. And then the one on the left is the potential image using the AM-KFM mode, and the one on the right is the FM-KFM mode. The one on the right has much more smooth imaging and lower noise, high detection limit, the much smaller detection limit. I actually have one more image I forgot to include, is that I actually scanned the same sample halfway using the AM mode and halfway using the KFM mode with the exact same feature. And then this way you can detect, you can see the comparison side by side. The FM is much more sensitive and much better. This is a single pass KFM imaging of a graphene. In this case, this graphene is not stripped from graphite. This graphene is generated by heat treating silicon carbide. And then here the aux number 3 is the DC-DC signal, which show you the low DC-DC signal on a single layer graphene area. So that's we use DC-DC signal to detect the layers of different graphenes, actually. This is this DC-DC imaging of metallic nanoparticles. These metallic nanoparticles are actually made of silver, and then DC-DC signal shows relatively strong signal on these silver nanoparticles. Let me mention some other small imaging mode that I come up with during my career of using the instrument, and this is called this AC modulation imaging using AFM. So AC modulation is that we could use different kinds of physics to modulate the sample to cause the sample to oscillate with different kind of force, for example, magnetic force or electrostatic force, and you can detect much different information from the sample itself. Let me, before I say that magnetic sample modulation, I will mention that this is actually not MFM. We're not detecting the magnetic domains or magnetic field. We're actually detecting magnetic response. And some of the soft magnetic materials actually does not have magnetic field. However, they will have magnetic response. So it's not MFM. It is magnetic response. In this case, we just use the part of the adjuvant AFM component. It's a mag sample plate, and then we use the AC current to drive an AC magnetic field, and then some of the molecules and then particles will actually be oscillated by the magnetic field, and we can use contact mode to detect this oscillation, and that allow you to detect the responding species such as particles and molecules. It's a kind of interesting application of using the existing hardware. This is a sample that we created to prove that concept. These are polystyrene particles, self-jam on the surface, and we put a drop of particle with different particles in it. For example, iron oxide or ferritin molecule. And then they actually assemble on the surface with hexagonal structure, and that's what it looked like. So the image on the right, we have topography of these iron oxide, and we have MSM, magnetic sample modulation amplitude and phase, and these are actually detecting the magnetic response of these iron oxide. And not only magnetic nanoparticles, some of the protein molecules also respond to the magnetic field. For example, here in this case, ferritin. Ferritin is a molecule that you can find. This is a protein molecule you find in the red blood cell. They have iron cores in it, and they also appear to look like rusty red. And surprisingly, no surprise, we can find out these protein molecule can also respond to magnetic oscillating field. Okay, so again, thank you for the time today. This is what we try to cover of some advanced imaging mode. And if you have questions, you can unmute yourself and ask me. And we have John Alexander in the audience. He's also the creator of that single pass KFM and then FM-KFM. So if you have advanced questions on the Kelvin force microscopy, and John is here to answer too. John, are you in the audience? Can you hear me?
Yes, I'm here.
Okay. I have a question about the FM-KFM. You take the phase signal output to be an input of second lock-in, or do you take the other signals? I'm a chemist, so those signals always confused me.
Yeah, basically we take the patent was on taking the phase signal from the first lock-in and using that as the input to the second lock-in or second and third lock-ins. The advantage of using the phase signal is that it, because it was calculated by the DSP in the Mac mode, it is purely phase. It has no amplitude components to it. So it was clean in that sense. It didn't have any, if the amplitude changed for some reason, it wasn't going to affect the phase. And the fact that the phase, basically the phase gives you an indication of how the resonant frequency of the cantilever is shifting. So that was the basic scheme. It was based on Lucas Eng's work at what is it? He was in University in Dresden, but they were pushing FM-KFM using a PLL, and their whole scheme ended up that they ended up bypassing the PLL and just pulling out the phase detection signal from their PLL and using that as the input to their lock-ins. So in our scheme, we pulled the phase signal from our lock-in and first lock-in and used that as the input signal to our lock-ins in the scene. So since Lucas Eng called this thing that was actually running on phase as a FM-KFM, we kept the same nomenclature, although I would have called it a phase modulation instead of frequency modulation in both cases.
Right. Because you see, the modulation of the primary resonant frequency is created by force gradient. It is modulated, but you actually don't lock onto it. You don't use PAL. How fast is the PAL? Is it too slow to lock on?
The PLL can be super fast. Actually, you can do heterodyne PLLs where you're operating at much higher frequencies than the resonance frequency, and you can theoretically measure the phase faster than a single cycle. So it's that part is fairly robust, and you can do it either digitally or in mixed analog, like we did at Agilent, or in right now our present design uses full digital controls for doing a similar heterodyne scheme. We're operating at much higher frequencies.
Okay. Yeah. So in application point of view, the AM is much more easy to operate. FM is difficult when your sample is not flat. What I find out when the tip is climbing up and down of rough sample, the shift because of climbing is actually cause of just mess up the entire
Yeah, that's definitely true. It's much more sensitive to if you accidentally hit the tip into the surface a little bit on the sharp edges of silicon. It really messes up it takes a while to recover because the signal gets out of whack temporarily while the phase recovers. And that's going to depend on the Q factor of the cantilever, how long it takes to settle back in after the disturbance.
This phase lock, it's because you're detecting the shifting of the resonant frequency. But if you're imaging rough sample, the slope also caused the resonant frequency to shift. So actually, there's a lot of topography effect. So I only use the FM on a very flat sample to detect some very small signals. When you use that big signals, it doesn't have any advantage anymore.
Well, I mean, in terms of accuracy, the FM signal or the FM technique is superior, just because the fact that basically you always get some cross coupling of the electrostatic signal in the cabling to the input deflection signal. And if you're doing the FM technique, you're not measuring that signal. You're measuring these side bands that are generated on the resonance frequency of the drive frequency of the cantilever. So it avoids the sensitivity to any cross coupling in the cabling, or cross coupling even externally through the sample or otherwise into the detector.
Yeah. So even when I do the FM, I always run the AM first and then run the FM and then try to push the resolution. It's in the application. I mean, I don't. I'm a chemist. I don't understand the signals and as much, and it's a struggle to read those. But in applications, yes, the AM is much more easy to do, and FM need to have a very, very flat sample.
Song, I have a quick question regarding the KFM. And it's actually very basic, I guess. What's kind of the ideal substrate for using the KFM? Because I'm just assuming that it has to be like semiconducting.
Yes. Yes. Yep. Yep. Yeah. If you use a metal like gold, and then the entire conductive is in physics we learn it just equalize the potential. The potential is completely equal. So yes, you have a very nice image of a piece of white sheet like this, nothing on it, no contrast, because the conductivity of the metal basically equalize all the potential around. When you do things on an insulator, like for example, on a piece of Teflon, okay, the problem of that, because it has very low capacitance, any little bit charge on it generates thousands of volts of potential. So in other words, it quickly overwhelms you. The entire KFM doesn't even work because either you have very strong charge or no charge, whatever it is. It had nothing to lock on. The charge is too strong. Yes, an ideal substrate is silicon, actually.
Okay. Yeah.
Yeah. And if you have like stainless steel, that's stainless steel is another thing people love to use KFM, is because stainless steel, if you polish the surface, you have grains, and then these grains exposed to different humidity, the chemical reactions, the electrochemical reactions cause the surface to have different patches of kind of potential. That's another thing. It's not substrate anymore. It is a sample. I like to study it. It's a stainless steel inside some kind of humidity. You can see a very interesting signals.
People like to look at that for corrosion.
Correct. Yes, corrosion.
On the subject of substrates, those fluoroalkanes materials, if you basically their potential displayed is caused by the dipole moment within the fluoroalkane molecule, because the one end of the chain is basically hydrogen terminated carbon, and the other end of the chain is fluorine terminated carbon. You end up with this, I think it's 3.6 dBi dipole at the center, along the axis of the molecule. And when they self-assemble, that all those dipoles end up lining up, and you end up with this potential difference. And depending on the substrate, you'll end up seeing a different surface potential difference. And part of that is the fact that when it's on silicon, which looks like these are on silicon, you end up with seeing an image charge formed in the silicon below the silicon oxide that tries to cancel out the potential of the dipole on that side. If you put the same material on mica, you end up with almost twice the surface potential difference between the mica region and the top of the these fluoroalkanes. Basically, just because in this case, it's caused by the dipole moment, and you basically are have a mirror charge that was canceling it out in one case. In the other case, you got some thick mica sample to a seal puck behind it, and it doesn't cancel it out in terms of the field that the tip is seeing near nearing this top surface.
Yeah, that's interesting. I never had that sample before with a mica substrate.
Yeah.
By the way, I'd like to mention, John, what's the name of your company? It's SPM Labs, right?
Yeah.
Yes, SPM Labs actually supply this particular sample to various AFM companies because this is a very interesting sample to use as a standard testing sample for Kelvin force microscopy. You can actually buy those samples from John Alexander's company. It's called SPM Labs.
Thanks for the plug.
Hopefully that, yeah, I heard that the Park Systems, this AFM company buy from you guys.
Yep, a lot of companies buy from us.
Can I buy you lunch and you give me one for free?
Kemi was saying something about you wanting to,
Yeah,
you using a lot of fluoroalkane samples.
yeah, I do have a plan. After Steve Raba finished his daughter's wedding, then I will visit you because now his head's somewhere else in the cloud. I can't find him. And then yes, I should buy some of this. Yeah, in the chat you can see John actually posted the link of that buying of that sample. It's www.spmlabs. There's s.com. Yeah, one comments to Jason and also another audience, Heidi. These advanced imaging modes are actually part of the hardware of we call it AC3 box, Max 3 or AC3. These AC3 boxes actually has 1, 2, 3 lock amplifiers. I don't think your Agilent AFM has the locking 3 amplifiers in your instruments, but those are a lot of fun to do because once you have 3 locking amplifiers, you can do far more experiments way beyond these advanced imaging mode, including a lot of advanced applications you can invent yourself. Yeah.
Yeah, I know. I only have the Mac mode on mine, and I did try at one time to take just one of those breakouts patch cords to try and take the signal from the phase and put it into another external lock-in amplifier and stuff, but it was getting too difficult to do and that, so kind of gave up on it.
Yeah, it was a lock-in 3. It's the Kelvin force is very interesting. It's suddenly the AFM image is no longer colorblind. There's information there, and then I try everything. It's part of anything that you try to identify certain chemicals or whatever it is. I try with Kelvin force, and then I did it with graphene, with different kind of nanotubes. You can differentiate nanotubes from metallic to non-metallic. Yeah, it's a lot of fun.
I think one of the earlier images that I remember seeing was in a paper, and that looks like it's John's colleague there, Sergey. I think he had wrote a paper, and basically it was showing the mica just being after freshly cleaved, being exposed in the atmosphere, and all of the oils and stuff depositing onto the surface, and you could start to see the surface potential image changing.
Yeah, I think that was a graphite sample that was cleaved, and yeah, it's really surprising how long, or basically you can measure how how long it takes to get for your sample to become contaminated.
Yeah,
I did something with gold, and I did not do the KFM because gold cannot, does not give you contrast. When you do gold, about 45 minutes, the surface just lost all its atomic steps, and then it started to form herringbone structure. Very much, you first you burn the gold with flame, so it's clean. You burn it off any contamination. Now you continue imaging, and then gradually it's just changing shape in about an hour.
but I know with one of my techniques that I use here in the lab with the XPS, I mean, you put anything in there and you're always going to have the adventitious carbon on the sample, and you use that to refer for your charge compensation to correct.
Yeah. It's surprisingly, if you keep a annealed gold in DI water, it will maintain its cleanness for much, much longer time. I have a comment from the audience, Amar Al Hamri, and he said, many thanks for the tutorial. Unfortunately, I did not catch the take from the beginning. When will the tutorial be available in YouTube? Just look at the presentation at the lower left corner. That's the URL of the YouTube channel. And this image, I will upload it as quick as possible. Basically, it is on my computer. I will edit this a little bit, and then I will upload to the YouTube through this channel. And we already have 6, 7 of these old presentations, and welcome to check it out. And you're always welcome to contact me if you have any questions, and if you happen to use Agile AFM, and we'd like to support you. If we are running out of questions, we'll see you next week. And again, next week, it's not going to be me. It will be Igor Sokolov, and talk about his experience with atomic force microscope, which is 34 years of experience. And hopefully he will say something about his ringing mode, because I need to learn that too. And thank you for your time. And if you have any questions, you can, I think I have, my email is songxu@nanoqtech.com, which is, you can follow the NanoQTech website, and I'll be happy to answer you. And thank you, and see you next week.